Hello and welcome to Build Your Own CPU Part 10. In this episode, we'll be looking at the T-state boards and the instruction set that they decode. Now these are the boards. There's one board for T-state 0, 1 and 12. It seems a bit odd order, but there was room on there to fit T12, so I squeezed it in to save another board. And then there's the half boards that do T2, 3, 4 and 5, and the other half board that does T8, 9, 10 and 11. They're all the setting up of the memory address register for the different memory address modes. Then we have the T6 board, which is the load the B register, with its bodge link in the middle, because I made a mistake. The final Gerber, I have that corrected. And we have the T14 boards. This instruction has got lots of possibilities, so we had to spread over two boards. So there's rule A to E on the first board and rules F to N on the last board. Again, this has got a few little mods on it as well, which will be fixed in a final Gerber file. Now these are the instructions. Move, which is move data from one place to another. Add, which means add one value to another. And there's subtract one value from the other. Then there's add with carry. This allows you to do 16-bit maths with an 8-bit processor. And there's sub with borrow, which again allows you to do 16-bit maths with an 8-bit processor. Then AND, which ANDs two values. XOR, which XORs them together. And number 8 is you can OR them together. Then we come to 9, which is an out instruction. Not only is there memory space in this, there's also output space, a bit like the Z80. So it uses the same address register, but it's sending out to physical hardware rather than just memory. Then there's logical shift right, which shifts a value to the right, and if it overflows out the bottom bit, it goes into the carry. There is no logical shift left because you can do that with just a simple add to itself. The in command is for bringing stuff in from an I/O device, like the keyboard. Then there's branch, which is branch to wherever you want in the memory. Then there's skip if the 0 flag is set, and that skips 2 bytes and allows you to do a test on the 0 flag and branch off whichever way it is, whether it's on or off. Then you've got skip if carry, which is the same thing but with a carry flag. That gives us 112 unique instructions if you take into consideration all the addressing modes. We went over this in the overview video in part 8. This is the overview of all the matrices. I've done a video sort of going over this, but this gives you a better view of the actual data lines. So on the left here, we have the demux boards, which we covered, which demultiplexes the destination modes, the source mode, and the instructions. And then we have the T-states feeding across from the motherboard. We don't have a T15 because we don't use it. And we don't use 7 and 13 either, but they're on the board here. 15's got a special use, which we'll come to when we come to the motherboard. And then there's the pulse signal as well. So these all feed up the long bus, which you saw on the left-hand side. And there's 40 signals there. The next boards, the T-state boards, do the actual decoding and tell the control lines what to do. They pick off the signals that they need from this long bus. It's a sort of a matrix, and you just pick off the ones you want. I didn't do all the possible holes that you could have there because there'd be too many holes for the circuit board because the manufacturers have got a limit on how many boards you can have. So I worked out what was needed and only put the pads where necessary. So here we've got the T0 and T1 and T12 board and 14 board, and then comes the other half boards and the T6 down here. These lines come from up here as well. I just couldn't fit me very well. There's multiple lines, not just 3. These boards generate 72 different signals. Fortunately, some of these signals will be on at the same time, so we can actually reduce that amount, as we'll see later as we go through the boards. We can reduce that down to 45 signals. So these outputs all feed into the OR bus matrix. Now again, this is just a long bus going up and down, and then you're picking off your signals. So there's 45 signals here to pick off, and you may find like a register that the T0 turns on, a T14 may turn on as well. So it ORs them together So you might have, say, the A register input enable could come from several places. So they would all go in and all be ordered into one and give one signal onto the signal bus. Thus, we reduce it down to 32 signals. If you look at the T0 and T1 logic, well, T0 and T1 are exactly the same on every instruction. So if we just look at the green bit here, this is a list of all the signals that need to be turned on in what T states. You've got the T states here and what signals need to be on when in those T states. There's one of these grids for every instruction and every addressing mode of every instruction. So there's 112 of these. But the first two here in green are identical on every instruction. This is read the program counter and load it into the memory address register, and the next line is to increment the program counter and fetch the instruction. So that's the same on all of them. We look at T0 and T0. T0 does these three all together, so we don't need to put three lines out. We can combine them into one line. So we have this signal, which goes to the OR bus line number 42. And you see on T1 state, we've got a lot of different things turned on, but they all come on at the same time. So we only need one signal for that, and that happens to go on bus line number 41. And then we've got, here's T2, 3, 4 and 5. This is the addressing mode. So you've got two possible addressing modes that this looks at. R1 and R2 addressing modes are not used in these states, but memory direct and immediate data modes are. So memory direct is source 0, so if you've got that one, or you've got immediate data, as in the next byte is on, and they come on and will send a signal out to all these. So A input, program counter output, memory address input, very similar to the T0. So that's for T2, but we can combine them into one signal, which is bus number 17. If we're doing it on the T3 state, well, we could have either of these addressing modes for the T3 state, so we bring that in here, save a bit of logic. When T3 is on, all these outputs come on, which is what's in that grid we saw earlier. And we feed all them together onto one line as well. Now, when we're doing the memory direct addressing mode, we go into T4s and T5s for that. We only need memory addressing mode for the source feeding into these. If we're on T4, we turn these signals on, and when we get to T5, we're going to turn those signals on, and we can combine them all onto those four there. So that's the addressing mode for the first source. Then we've got 8, 9, 10, 11, which is exactly the same circuit, but this time we've got the destination, which is also the second source, but it's also the destination. So again, we can combine those signals together. We can combine these signals together, and these ones, and these ones. So we only need 4 signals going up the OR bus for all of these. Now, if we go to T6, now this one's a bit more complicated. T6 is the loading of the B register, and there's 5 places that can be loaded from. We've got memory direct, as in the memory address register is pointing at the address of where the data is. When that's on, and we've got T6 on, then we're going to do a data input and a read. So we're coming in from memory, so that the external data bus is connected to the internal data bus to read outside data in, and we're doing a read, and that signal feeds down to these 2 AND gates as well. So we've got an in instruction here. If we're not doing an in instruction, as it's a move or add, etc., then the memory chip select comes on. And in is for the I/O, so that's not an I/O, must be memory, so memory chip select comes on. If the in instruction, which is instruction 11, is on, then this one won't come on, and we'll get an I/O signal to say it's an I/O signal we want, an input, rather than memory. So that's that simple bit of logic. And of course we can do this for immediate mode as well. So you can read, well, immediate mode will only ever be for memory really, because that's the next byte of memory. But we don't need any more decoding logic. We're just getting the data for the B register from R1. If we're in addressing mode 1, which is R1, and we've got T6 on, then we'll do an R1 is put out that goes into the B register. Oh no, we'll come to this bit in a minute. And R2 is the same, so we can put R2 straight into the B register. So R2 output goes into the B input. And then we've got the next addressing mode, the fifth one, or fifth input I should say, where we've got T6 is coming on. And we only use this one when we're doing a skip if 0 or skip if carry. So if either of those are on, then we lose this signal here and we can't come in from R1. This bit could have been put onto R2, but I'll explain why it's not in a moment. So if we're using either of those, we invert it again. So if skip if 0 or skip if carry, then move the program counter output into the B register. Because what we're going to do is we're going to add 2 to the program counter to do the skip, or add a 0 if it's not true. Now when we do the skip instructions, we have to set an addressing mode. All instructions have got addressing mode, even though they don't need it. So they're set to use R1. So S1 will come on. But because we've got this signal coming up here, it stops the signal coming through and doesn't turn on the R1 register. I mean, if we add an illegal instruction and add R2 turned on, then it will turn R2 on as well. So we make sure we don't do that. You think, well, why don't I just leave them as zeros on the addressing mode? Because that would not, you could put this signal here up into this AND gate, so the memory direct addressing mode wouldn't come on. Yeah, but unfortunately, when you use a memory addressing mode, that also increments the program counter, which we don't want to do. So we use the R1 instead. It was just a sort of a cheeky bodge. Again, these signals, that one just goes straight out to there. These two are combined for there, and we use a few more there. So these are all the actual lines it goes out to. T12. It starts to get more complicated. Well, it isn't that much more complicated. What it is these 7 instructions are just all ORed together. This is a different way of doing a big OR. Just saves a few transistors. So that's a 6 input OR gate and that's a 2 input OR gate. I didn't take the OR gates above 3 inputs because you've got too many transistors sitting on top of each other and I didn't know how well it would work, so I limited it to 3. If all 7 of those are on, and it's a T12 that comes on, then we'll get this signal coming out here. Now this signal feeds several places. You want to turn on A input enable because T12 is all about loading the A register. If we're doing a skip with 0 or skip with carry or a branch instruction, they all get fed through here as well, through these OR gates. So if any of these instructions are on, then the A input enable will come on the T12. If any of these instructions are on, these 7 are on, that signal feeds down here, and it says, well, if you do one of those instructions, you've got an addressing mode D0, you need to have these signals on as well, because you don't need that with these instructions. That's why they're not included in this list up here. So those 7 can all use that addressing mode. This is the destination addressing mode, so it needs to turn those signals on. And the same here, if you're using R1 for the destination, you need that one, or R2, you need this one. So that's R1 output or R2 output. So that logic there can feed 2 lots of signals. And this one down here, as you see from these 2 signals here, they come from the sub with borrow and add with carry. that means you need the C register. So those come on, and if T12 is on, then the C register input enable is turned on. And that means the carry flag will transfer into the C register because you'll be needing the carry flag for those two instructions. Don't get it confused with this flag. That's the carry, this is the C register. The carry output is directly connected to the C register and is always available unless when this signal comes on, it transfers. This is sending the signal out for doing your skip instructions. They all go down your bus. So all these three are connected together on one. They're all going out, got their own lines. There's 50 of these lines in total. So if we go to the next one, which is T14A. T14 is where all the action happens. This is the actual execute of the command. All of the others were for setting up the data. So if we start at the top, got a branch, or an out, or skip for 0, or skip for carry. They're all together, or not together. This is it's a bit up the other way. I'm doing these actually NORs. So if any of those four are turned on, then we don't want the Z input enable or 0 input enable because these don't affect the 0 flag. So 0 input enable is turned off. So if any of those come on, we lose signals and that doesn't come on. Again, it's triggered by T14 through there. So this is inverted logic for them. So if it's any of the other instructions, this will be on. So if we're not using Z out, and we're using destination of R1, then R1 input enable is on. So don't think of this as Z output, think of 0 output, think of this as not these instructions. So if it's one of the other instructions, this will come on, and if you go into R1, then this will come on. So you're talking like move, add, sub, and all the others. It will turn the R1 input enable register on. Or R2 for this one. Or if you're going to memory direct for D0, it will turn memory chip select on, taking right the data to memory. There's no immediate on the destination, because that would be the next byte in memory, which would be program code. And you've got a pulse. The pulse signal comes in here, and this is ANDed with the memory chip select signal here. And the idea of this is on actual memory chips, very often you can have the chip select turned on, and when the chip select is turned off, that's when the data gets strobed into the chip. So with the pulse off to start with, all the address lines and everything get set up, and the pulse comes on to chip select on the actual memory chip, and then when the pulse goes off, that strobes it into the memory. So you can use your memory chip select as your strobe into your physical memory chip or device. If you're doing a move or an in instruction, they're all here. And the out instruction, so the lines come down here, it's difficult to see. So if you do moving a move, in or out, this comes on, or let's follow that line across, it's difficult to read. Or a branch. There's another OR that's basically a 4-input OR gate. And you've got T14 on, that's T14 line. Then we're sending data out of the B register. So the B register, the data comes out there if you're doing a branch, an out, a move, or an in. And then the next bit down, we've got this data out enable. So if we've got the memory chip select signals going to be coming on, we'll also be wanting to send it out the data bus, to the external data bus. So we've got to switch that to output mode. So we've got the out instruction, we'll turn that on. And that one's the T14. So if we're doing an out instruction, turn that on. Or if we're doing a memory write instruction, turn that one on. Now if we're doing an out instruction, and that one's T14, then we want to turn no, it's not T14, that's the pulse, sorry. So we've got pulse, the out instruction, we want the I/O signal to come on. So this one will strobe with the pulse the same way as the memory chip select will strobe. So that can be used for strobing data into the output device. Now we've got the program counter input enable. That would be used on the skip if zero, skip if carry, or the branch instruction, because either of those three instructions move data into the program counter. So the branch is basically use this address, bang, straight into the program counter. The skip if zero and skip if carry actually adds a 2 to the program counter to make it skip 2 bytes. So that's those three there, and the T14 signal coming in, bang, put the information straight into the program counter, and then the next instruction will carry on from there. If you're doing a sub or sub B, you've got to tell the adder that it's got to be a subtract and not an add. So you turn the sub signal to the adder on, so it knows to invert the signals to do 2's complement addition to give you a subtraction. There is an add one, we'll see that in a while. So we've got that one, these are the bus pin connections going out, so there's one for each on that one. We didn't save any pins on that one. 14F, the letters come from the rules I'd add, rule A, rule B, rule C, so forth. Well, this first one in here is rule F. So here's the add I was on about. So if you're doing an add or add with carry, or we're doing a skip with zero or skip with carry, they'll get pulled through and that will turn the add on, because all four of those tell the adder to do an add. And there's your T14 to tell it to do it, only on T14. So that will be off on any other T state. If you're doing any of these, and or you're doing any of the subtractions, so to come in here, big OR gate, you need the adder output to be turned on. So any of those instructions, the adder comes on. On T14 that is. The adder output does come on other cycles, T1, T5 and T9 I believe, but that's all to do with incrementing the program counter, which isn't an instruction, it's an addressing mode. So do we want the carry input enable on? Well, for these instructions, not for those two instructions, but let's see what we've got. We've got add and sub and add with carry. Any of those three are on. On this one is sub with borrow. So any of those two or those two, get OR through, and when T14 comes on, the carry input is enabled in case any of those call to carry. Also here, boarding with them, is the logical shift right. So if you're doing a logical shift right, then the bit 0 gets moved into the carry, so you need the carry input enable turned on. Now here we got C set stroke increment. This flag's turned on when you want to increment something or set the C register. So if we're doing a subtraction, we need the C register turned on. So T14, and that comes on, sets that on for subtractions. Not sub with borrow, because that needs whatever is in the carry flag to have come through. It's just ordinary sub. So that's the only place that's used apart from when you're incrementing on the addressing modes and the fetch instructions. And here we've got whether you want it clear or not. So if you're doing an add or a skip if 0 or skip if carry, then you want to set C register to 0. So you just add a 0 with those. When you're doing a skip if carry, you're not actually using the carry put into the clear register, it's getting fed into D1. So you want your C register to be 0 because the values for these gets fed into the B register to be added to the A register. Alright, next one down is the logical shift right output enable. So that's quite easy. Logical shift right instruction and T14. So take the output from the logical shift right register. That puts that straight on the data bus. And then we've got, if you want to do XOR, or AND, again, they're nice simple ones. Just turn the particular output on from those cards. There you go. And that's all those buses positions, one for each of those as well. Here we have the top OR gate. So here's all the OR gates on it. It's just all OR gates. So you've got 2 3s feeding into a 2, so that gives you a 6 input OR gate going out. And then we've got 5 on the next one. And then this one here can be a 5, or it could be a 3 and a 2, depending on the links. And we can have a 3 and a 2 or 5, again, depending on the links. And then these bottom ones are just passed straight through. As you see here, T0 has got an A input enable. T2 has as well, and T4, 8, 10, 12. So those 6 signals that are on the OR bus, we don't need to send 6 signals out to the A register. We only want to send 1. So we OR them all together. They're coming in the OR bus on those numbers. Oops. To there, and they all connect onto this port of the board and all get joined together and give one control signal out. So these are all the control signals. And again, with the add output, it can be used on either any of those 4 states. So there's the signals coming in, and they all get added together. It only uses 4 on this one, so what we do here is we just link these 2 together to make this OR gate come on. And then on the next one, that just uses 2. It's A output enable. It uses these 2 here, and again we'll just link that one across, because this will do something different on one of the other OR gate boards. And we'll put a link across here, so this signal will come straight out of there. And then we've got the B output enable signals, 2 of those, which get all together here, and that link's missing, so that will come straight out here to there. No control signal. And again for R1 output enable, so we'll have 2 here, the link across there, straight out to that one, R1 output enable. And then we'll have 2 here for R2 on T6 and T12. Those 2 are all together out here to R2 output enable. And the other ones down here, there's only 1 of them, so they just pass straight through. I just use this card to reach from this bus to the other bus, so it's a direct link across. And there's LEDs on there, so you can see when the signals come on or not. If we go to the middle one, so we've got 5 memory address register input enable signals. They come on and all get all together. And we've got data in enable signals. It's 4 of those, all together. Then program counter output enable again. You notice that like you've got bus 42 there and bus 42 here. You know, I mentioned on the T state cards on T0, it feeds 3 different places. Well, there's one of the places it feeds, and there's the other. So we can just pick off the same signal for them. As you notice, there's a 17 there as well. It's the same signal, duplicated. And then we got 4 more there. So in this case, here we've got 4 inputs there. 1, 2, 3, we link across for 4. And we put the link on this one now. So all of these get ordered all together, and we come out of here, and that signal's just not used. Then again, for those 4, linked across B. So they're all joined together for that, and the other ones just come straight through. And if we look at the bottom OR gate, again, it's exactly the same card. And we've got all the memory chip selects put together, and all the reads together, and all the selects, as you've seen in the previous one, and the odd ones at the end. These all clump together and go through there, and so forth. And there's your control signals. On this board, we've got B linked on this one, because there's 4 of them together. On this one, we've got A linked, because we've got 2 separate ORs. So I've got one board, does 3 different functions, and then we've got a couple of spares straight through the bottom. I think that's enough brain bending for one video. I should be putting the Gerber files for all these boards and associated documentation online soon, just as soon as I've got it all sorted out together, and some of the bodge wires and that fixed on the actual boards. So if you used to build one of these, you wouldn't have to do the bodges that I've done. So don't forget to like and subscribe and tell all your friends, and hopefully I'll see you in part 11.